tell me your name?
Andrew Fountain.
Okay, and what are you doing here in Antarctica?
I study the glaciers of the dry valleys.
And what is it that you study about them?
Well, there's two things actually. One is that we just study the change of the glaciers, whether they're growing bigger or smaller. That includes, it's a more subtle aspect of it, are they increasing or decreasing in mass? That's what we're really interested in. But then that gets manifested as them getting larger or smaller. And the difference is there's a dynamic response. There's a mass change, and then at some time later, the glacier changes.
How do you measure the mass change of a glacier? That's a huge...
Well, actually, it's as simple as a ruler, because what we do is we put stakes into the ice, and then if the surface lowers relative to the stake, so the stake looks like it's becoming longer, we know we're losing mass. And conversely, if snow accumulates on the stake, against the stake looks like it's getting shorter, then we have mass accumulation. And if we know the density of the surface, we measure that. Then we know then we add all these up and average them, and then we know if the glacier is increasing in mass or decreasing in mass.
So a glacier is going to have the same kind of, take up the same kind of distance based on its thickness? I'm just, how do you measure how far it's creeping forward?
Yeah, that's right. Glaciers obviously flow downhill, and they're constrained at the upper end by the mountain, so the only place it can go is downhill. So we really only have to measure the perimeter of the glacier at the down valley end of it, and we can see it, well, we can measure it going forward or going backward. Back in the States and elsewhere in the world, these glaciers are retreating really rapidly, so literally by going out in every year, just maybe surveying the perimeter of the glacier, and then coming back next year surveying the perimeter again, you can see the change quite easily. Here, the changes are so small that the only realistic way for us to do it, the only realistic way for us to do it right now is through photography, comparing it to the old photographs. I mean, we can survey it, but we wouldn't get any good data for another 20 years, so we kind of have to rely on what's been happening in the past. And since there wasn't survey data back in the past, we have to rely on photographs, which show us essentially that these glaciers aren't changing.
And how did you get into doing this? How did you first?
Like in the subject or down
Down
here?
in Antarctica.
Oh, so see, this is part of a larger project, this LTER project, long-term ecological research. So my colleagues are studying the ecosystem in this valley, which is, there's no higher plants or animals. It's all microbes, basically. But what drives the whole thing is water from the glaciers. Without the glaciers melting each summer a little bit, you wouldn't have any water, and therefore you wouldn't have any ecosystem. So I was asked to join the group of biologists to identify the processes that control water flow from the glaciers. And that's the other thing that I do. The mass change of the glaciers, and that's kind of a climate change issue. But then the real thing that I'm hired to do is try to understand how these glaciers melt and supply water to the ephemeral streams and the ice-covered lakes in the valley.
So when you say ecosystem, that's meaning the life that's down there?
Yes.
And what's special about the ecosystem in the dry valleys?
Well, there's two things actually. Like I said, it's microbially dominated. No place else on Earth isn't microbially dominated. As soon as you get plants or higher animals, they become the main parts of the ecosystem around which the microbes sort of play against. Here, it's only microbes, and they're only kind of dealing with each other. And microbes as in phytoplankton in the lakes, there's some algae in the streams, and then in the soils there are these small worm-like critters called nematodes. So these guys all kind of interact. So that's part A. It's a microbially dominated ecosystem, which is highly unusual. Plus, the dry valleys is basically the last terrestrial ecosystem on Earth. If you go any further south, it all becomes ice covered. So we're really at the limit of terrestrial life forms. And I don't mean just bacteria sitting there. I mean terrestrial life forms in an ecosystem of lakes, soils, and streams. So it's that interaction. If it gets a little bit colder, everything's kind of shut down and covered with ice.
Would you say that this is, some of the people I talked to sort of described it as an interesting place to do research because it's kind of a simplified ecosystem, so you can break down really basic aspects of the ecosystem. Would you say that, or would you
Yeah.
describe it in a different way?
No, I think that's accurate. You know, it's not simple, but it's simplified. And the advantage we have is that we can essentially draw a box around it and say this is the ecosystem, whereas back home, you have birds flying through, you know, you have deer walking through. It's sort of hard to say, you know, this is a contained system because there's so much flux in and out of this thing. So here we are, and we can hopefully actually identify the entire cycle of nutrients through this system, carbon or phosphorus or what have you. And you can't do that anywhere else. So we might be able to identify some basic processes, some basic ecological processes of how nutrients move through the system that you can't do anywhere else.
And what's the benefit of doing that?
Well, that's going to the basis of ecosystem function and how does carbon move through the ecosystem. That's kind of the main issue, really. Yeah, I mean, the nematodes were, for example, you know, we have 3 species down here, and back home there's hundreds. You know, so by having a simplified system, we can really look at how these different microbes exchange the energy and exchange the nutrients.
And so you've got these met stations all over the place.
Mhm.
Can you tell me a little bit about the history of that and why they were?
The meteorological stations were put in almost 14 years ago at the start of the project, where we're trying to define the climatic, or I should say the meteorological environment of the valleys. And because we were unsure what the environment was like. There had been past measurements, but it's been like a single station in some other valley or something. And of course we're interested on how the weather would change along the valley axis and with altitude up the valley sides. Because putting a meteorological station in the valley bottom, you might have differences up on the glacier where we're getting the water from. So we put a number of stations in the valley. We have eight in Taylor Valley, and then we have 3 other stations elsewhere in adjacent valleys. And we've been using that to identify what the environment is like. And it's actually turned out to be very interesting in 2 aspects. One is we found that, believe it or not, the temperature, air temperature, gets warmer as you go inland towards the ice sheet. You'd expect the exact opposite. Oh, there's the ice sheet, it must be colder. There's the shoreline, it must be warmer. It's the exact opposite. And that's because the air, well, it's actually the air comes off the sea ice, which is fairly cold and moves in the valley, versus the air that drains off of the ice sheet, and as it drains down into the valley, it actually heats up. So the air coming from the ice sheet in many cases is actually a little bit warmer than the air coming in from the coast that's already cold from that ice. So that's one thing. And the other thing, like you just mentioned, is katabatic winds. Climate change for us could be a change in the frequency of katabatic winds, because we found that for every 10%, how's the word? Yeah, for every 10% change in the frequency of katabatic winds. So in other words, if it goes from, say in the wintertime, it goes from 40% of the time katabatic winds to 50%, the average temperature in the valley will increase by a degree.
Wow.
That's because the winds are coming down, heating up as they come down to lower elevations. And there's very good physical reasons why this happens. And then warms up the valley bottom. So if we have more of those winds, as far as our temperature gauges are concerned, we're having a warming. So if we have more of those winds, it gets warmer.
Right.
So our climate change could be just wind change.
Wow.
So-
And the ecosystem can handle that much of a change?
Well, yeah, we'll see, won't we? In the wintertime, it doesn't really matter too much whether the temperature goes from -40 to -30. You know, everything's kind of sleeping anyway. But in the summertime, that could mean the difference between meltwater and no meltwater. So it's kind of like this abrupt change, you know, nothing, bang, meltwater. So
Right.
that's where it would